Hello everyone. Today we will discuss what are the other possibilities of encoding numbers using binary. So, let's reiterate the problem when we were doing the initial lectures. So we have seen that in a binary number, let's say it's a 4-bit binary number, it has 16 different possible arrangements. Okay, so each of this arrangement of 4-bit could correspond to a number. And during our initial discussions of unsigned binary numbers, unsigned numbers, and again signed numbers, like representing negative numbers using different ways, we have observed that there are various possibilities. Now, we would like to raise this question again, that is there any other possibility to represent unsigned numbers using these, let's say, 4-bit binary numbers? Okay, so which arrangement should be there? One thing is clear, that it has to be one-to-one mapping, that each of the 4-bit binary arrangement should map to one decimal number. Okay, which decimal number? That's a good question, and that is the question we would try to answer here. And the numbers which we have studied so far, the representation we have studied so far, they are all called positional number system, because each symbol at a particular position has a certain weights to it. So that was a standard weighted positional system. And now, can there be merit or advantage in having some other system, some other way of representing same binary numbers? Like in binary numbers, can we have in a when we rephrase it in another word? So basically, in the binary, is there any other mechanism or any other mapping to map these numbers, these binary numbers, to any other two decimal numbers? Or should we conclude that the positional number system which we have studied so far is the only method, is the best method of representing decimal numbers or representing numbers using binary? Okay, so let us pose one question, that why are we representing decimal numbers in binary in a particular way? So the problem is, we would like to represent any kind of a number which we understand that this is a number. So let's say we want to represent 10, 20 or 1000 in binary. So the method so far we have learned, that let us convert this decimal number into a positional binary number by dividing it by 2, finding the remainder, again dividing it by 2, again finding remainder. So this whole process of converting a decimal number into binary number is a procedure in itself, which we have to learn. And if we want to develop in hardware, we have to design an hardware such that each decimal number can be represented into binary numbers. So this procedure, once it is done, then the numbers are represented in positional binary system. Then we can do addition, subtraction and everything. But again, when we would like to represent it back to humans, because as a human we understand only decimal numbers, although in our first class we have also seen there are various different number systems, like base 12, base 15 or Roman numbers which are there. But let's assume for the sake of convenience that decimal numbers are the standardized way of representing numbers now. And we as a human, our eyes are more accustomed to look at decimal numbers, to understand these decimal numbers, to see them in magnitude, to see them in quantity, and comparing them, doing arithmetic operations. So whenever computer would like to show us back the numbers, it again has to convert that binary number into decimal number and then show it back. So is there or can there be any other method which is more convenient, which can solve this particular problem, that we would like to represent the number. See, the problem is we have to represent the numbers in binary. Why we are using only positional number system? So let's explore some other ways. So one convenient or intuitive method which seems to be there, that we have in a decimal number, each digit has 10 different symbols: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So why can't we represent all of these 10 different symbols using 4-bit binary number? Because to represent 10 different symbols we would require 4 bits. Can we use these 4 bits to represent this each of the digit, and then we represent a whole number using collection of these 4 digits? If we represent in this way, we will call these numbers as BCD, or binary coded decimal number system. Okay, so in the simplest form, let us say let's say see this example. We would like to represent 5682 as a binary number. So we can represent like 5 as 0101, 6 as 0110, 8 as 1000, and 2 as 0010. So these are the standard representation in our positional number system. Also in positional number system we represent all these symbols like this. So we simply concatenate all of these numbers, and we say that to represent 4-digit decimal number we would require 16-bit binary number. Okay, so that means whatever number of digits are there in decimal number, we multiply it by 4, and that many number of bits are required to represent it in binary. This particular form of representing is simple, intuitive, and it would work quite well, because we are able to see these numbers, and the most important thing is that the way we visualize numbers, we can easily visualize these numbers. We just need to break them into group of 4 we call nibbles. So if we break them in nibbles, and then we can directly recognize it as a decimal number. Now this particular form, like one more interesting thing here, that here in using 4 bits we can have 16 different combinations. So which of the 16 combinations should be mapped to each of these 10 symbols we have in decimal? That's also a good question. So let us say this particular representation we call 8421, because each binary digit will have a weight. So for example, the first bit will have a weight of 1, the second bit has a weight of 2, and third bit has a weight of 4, and fourth bit has a weight of 8. So because each digit represent different weights, so that's why it is also called 8421 BCD numbers. So this is the most convenient, most standard BCD representation, and each decimal number or each decimal digit is represented by a bit of 4. So this BCD representation is quite interesting, useful, because it is most intuitive. There is a one-to-one mapping. So if we have any decimal number, we can quickly, we need not to have a kind of a conversion formula, or that divide by 2 decimal things, or some algebraic procedure. But given a decimal number, we can directly represent them in binary. So there is only one lookup table. So for each symbol we have to replace it with 4 group of bits. So far, so this is so interesting, or so far, that when we build our initial computers, generation 1, generation 2, in those computers we could not even think of the positional binary system what we have currently. So at that time, because the only requirement of a computer was that it has to have discrete discontinuous digits, and decimal digits are and also it has to be it has to work with 0 and 1 binary system. These BCD numbers were satisfying both of these criteria. That is why in initial computers we were using these BCD numbers, and several BCD numbers were invented in that era, so which had certain advantages and disadvantages. So because of this intuitiveness, wherever we just need to represent number. Okay, now what is the disadvantage? That for representing it is good, it is sufficient, but when it comes to arithmetic means addition, multiplication, subtraction, these BCD numbers would be slightly complicated, because you have gap of these 6 numbers. So let's say I want to do addition. Now in addition I am taking some example. So let's say I want to add 56 and 75. Now if I am trying to do addition using BCD, so with this example we'll be able to understand that what kind of challenges we'll see. So when we want to do addition of 5, 6 and 75, or any two particular numbers, first thing we have to do is we have to represent them using BCD. So 5 would be represented using 0, 1, 0, 1, and 6 would be represented using 0, 1, 1, 0, and 7 would be represented using 0, 1, 1, 0, 0, 1, 1, 1, and 5 would be represented using 0, 1, 0, 1. Now we want to add, so we will align them. So basically 5 would be just below 6 and 7 would be just below 5, and we can use the same binary addition rules which we have learned for our addition, binary addition. So that means 1 plus 0 will become 1, again 1 plus 0 will become 1, 1 plus 1 will become 0, and there is a carry of 1, and that carry will come here. Now similarly 1 plus 1 is 0, carry of 1, 1 plus 1 is 0, carry of 1, 1 plus 1 plus 1 is 1 and carry of 1, and carry comes here. Now both of these numbers cannot be represented, is not a correct representation of our binary BCD numbers. In BCD the maximum or the largest digit could be 1001, that means 9, and so to make this correction, what we need to do is we need to add 6 to this output. Why 6? Because now the maximum number was 9, and if anything which is more than 9, if I add 6, then it will make it correct. So for example we'll see using this. So we will, if output of my binary addition is more than 9, then I have to add 6 to that particular nibble. Okay, so after adding 6, so for example the output was like after adding two BCD numbers here, the output 6 plus 5 will become 11. Now 11 is more than 9. Now if I'll add 6 to it, then it will become 1 and a carry will also be generated. So let's see here. So 1 plus 0 is 1, and 1 plus 1 is 0, carry of 1. Carry of 1 plus 1 equal to 0, another carry is generated. Carry plus 1 equal to 0, another carry is generated, and that carry would be added here. Okay, so rest of the addition, 0 plus 1 is 1, 1 plus 1 is 0, another carry is generated, 1 plus 0 is 1 plus a carry of 1 plus this one equal to 0, and carry of 1 is generated. So this gives us the correct results. This we can say is another 4-bit BCD number that would represent 1, and this is 3, this is 1. So after this correction of adding 6, we will receive the correct addition result. And when these 6 need to be added, So 6 need to be added in two cases. One, if the output of addition of a nibble is more than 9, or if carry is generated. So for example, there is a number 9 here, number 9 here, 9 and 9 both are added, it become 16. 9 plus 9, 2 are added, become 18, and 18 is more than 16, so that means a carry would be generated here. So if there is a carry which is generated out of addition of two nibbles, or the sum of two nibbles is more than 9, then 6 would be added. Okay, and the other thing is, whatever carry, so let's say a carry is generated in this, there are two additions which we have to understand, which we are doing. In the first addition, if carry is generated, then carry would be added by the carry would be added to the second nibble, and while doing the second addition of correction, like where to each nibble 6 would be added if the sum is more than 9, then also if carry is generated, that carry would be propagated to next nibble. Okay, so essentially each BCD addition would require two addition steps. One is a standard addition, standard binary addition. The second would be based on the condition. There are two conditions. One, if sum is more than 9, or if carry is generated because of that particular nibble, then 6 would be added in that nibble or result of that nibble. So in this way, BCD addition would work perfectly fine. So after these two steps, we can do addition. Similarly, if we want to do subtraction, if I want to do subtraction, then also the similar steps would be required. There would be a correction that is needed. So here we can see that for representing BCD numbers, representing decimal numbers, this BCD number system is good. Even for addition, the number of additional steps are minimal and thus can be used. But if you want to do multiplication, if you want to do division, the number of overhead, amount of overhead is going to be non-significant, because every time we have to take into account, essentially we are working with a base of 2 in with a system where base is 2 but actual base is 10. So that will always, we have to apply these correction factors whenever we are doing multiplication, division, subtraction. Okay, but still because earlier computers, they were handling very small amount of computation, and at that time the advancement in hardware was not that optimal. So that's why at that time they were still willing to use BCD numbers in the computers itself. So even this the example that IBM 360 which I gave, it was a computer which was a second generation mainframe computer, which whose life was more than 10 years, but only after integrated circuits were invented and third generation microcomputers were invented, then we shifted completely to a positional number system. Okay, so but during that era where BCD numbers were used in computer, they also invented some other representation which can overcome these like additional steps or some shortcomings of this 8421 representation of BCD numbers. So I'll give one at least as an example here. One which is quite popular was XS3 codes. In XS3 codes, this I'm covering this as a part of this lecture just to understand or just to see the beauty of representation and what kind of things we can do with the representation. So here like whatever standard BCD or 8421 BCD was giving, plus 3 was added. So 0 was represented using 0011 and 1 was represented using 0100, and so on for the rest of the elements. So we can again recall this particular thing, that using 4 bits we can have 16 different representation, but out of those 16 we need to select only 9 symbols. So basically for these 9 symbols we need to find which mapping is going to give us the best results. So one of these mapping is this XS3 code. The beauty of this XS3 code is it has a very nice beautiful property which is called self-complementing. So if you see here, let's say I want to invert this particular bit 1. So if I invert all the bits here, what I will get is 1 0 1 1. And let us see what do I represent using 1 0 1 1. So 1 0 1 1 is represented using 8. 8 is represented using 1 0 1 1. So the beauty here is 8 plus 1 is going to be 9. Similarly, we can do this particular experiment with any of this bit. We will find that when we invert all the 4 bits, then the output is 9 minus that particular number. So this particular property is called self-complementing property, and it is a very useful property whenever we are doing subtraction. So you have seen in 2's complement numbers also, they were also complementing, self-complementing. So whenever we were inverting them, or we were finding complement of them, then we were representing we wanted to have 2's power n minus that particular number as a complementing number. Okay, so here also we are achieving the same thing. Let's say we want to do subtraction, then what we can do is we can do the complement of that number and then use the addition to do subtraction. So that way I can do addition and subtraction using the same code just by inverting the numbers. The other thing is in our previous 8421 representation, sometimes we had to add 6, sometimes we need not to add 6. Here the problem has been simplified, that in some cases here we need to add 3 or we have to subtract 3 to fix the final results. Okay, so this according to hardware generation, it is found to be simpler if addition and subtraction is done using this XS3 code. One more thing we have to understand, that all of these codes are mostly invisible to the software developer or to the end user. It's only internal hardware representation, so it doesn't matter that whether 0 is represented using 0000 or 0011. One additional place where people have used this XS3 code is because here 0000 as well as 1111 was not used in encoding, so they could use all of these things to represent errors or to represent some kind of issues. So those issues could be reported. Let's say there was in the communication there was an error, so it could be reported using the symbol 1111, which means that some error has occurred in the communication or computation. So this way this form and another representation of our BCD numbers. Now, can there be something other possibilities? So let's see that if my challenge is that I want to design an error resilient code. So I am working over a noisy channel that if I'll transmit some number, in the end I should receive the same number. So and there is a lot of noise in the channel. That means 0 could flip to 1 or 1 could again flip back to 0. So if I want to make sure that such kind of errors doesn't happen, so we introduce some sort of redundancy. So this 2 out of 4 code is also a BCD representation, because I can represent again these 10 symbols using this 2 out of 5 code. Here the property is that each of this code is 5-bit code and only 2 ones are there, but these 2 ones are at different positions. So if at the output of channel these the output is not 2 ones but only 1 or 3 ones or 4 ones. So that means some error has occurred, and we can ask our system to resend the information. So this way it at least as a error detection system. So error could be detected with a greater probability that there is some error that has happened. Okay, so here also there are only these 10 combinations, and we have choose that which combination we would use to represent symbol 0, symbol 1, symbol 2 or symbol 9. So this is how for error resilient we can use some different kind of encoding. Now there is one more scenario, that let's say we wanted to reduce the power. Now how do we reduce the power? We say that the adjacent transition between adjacent numbers should be minimum. Okay, so let us say this is the property of a low power design or a low power system, that number of transitions should be minimized, and number of transitions cannot be minimized than 1. So we make sure that whenever we are incrementing a number 0 to 1, total number of transitions are at most 1. Okay, or always equal to 1 whenever we are incrementing a number. So here you can observe that if this is the representation of 0 and 1, the number of transitions are 1, and from 1 to 2 again the number of transition is 1, only this particular bit is flipping, and from 2 to 3 again only this bit get flipped, so number of transitions is still 1. So from 3 to 4 also this particular bit will get flipped, only one bit is flipping. Otherwise, if you remember, from 3 to 4 there would be 3 bits that would flip in a positional number system or a conventional binary number system. Okay, so in this binary, in this gray code, we will have only one bit flip from 0 to 1. Okay, so again let's say we want to represent only 10 digits from this 4-bit numbers, then we could have several combinations possible. Okay, but it is not that, if I have these 4-bit numbers or 4-bit binary number, I can essentially have all the 16 combinations of gray codes or gray numbers. I can have 16 different symbols. Even gray code is generic enough that if I want to represent, let's say 32 different symbols or 32 numbers, I can still represent it using gray code. The only thing is encoding is slightly different. So in our digital design, we use these gray codes whenever we would like to reduce the number of transition between the adjacent numbers. Okay, so if we would like to get a generic method of writing these gray codes, so this table could help. So these are gray codes for up to 16 numbers. So here you will find one interesting property, that 0 is represented like this, and then 1, and then 1 1 is representing 2, and 1 0 is representing 3. So this is also same here. Now after 3 we have made this the next digit, third digit, as 1. So this become 4, and rest of the thing is essentially in the inverse order whatever we have done here. So this will become 1 1, then 0 1, and then 0 0. The next I want to represent, after this is 4 5 6 7, I want to represent now 8. So for representing 8, I'll make the MSB as 1, and then will again, so this from 8 to 12, 8 to 16, it's again the mirror image of 0 to 7 numbers. So that means my 8 is represented using 1 1 0 0, and then 1 1 0 1 is the image of this, and 1 1 1 1 is the image of this. So that way, like in the reverse order, we keep on following all these numbers, so we can get 8 9 10 11 12 13 14 15. So similarly from 15, if I want to get up to 32 numbers, so the reverse, the order of the numbers would be reverse in this order by adding one more 1 here, and after that we'll go in the reverse order. Only the MSB would be 1 and the rest of the numbers would be in the reverse order of 0 to 15. So this way we can represent any size grayscale gray code numbers. Okay, the overall conclusion here is that if I want to represent any number, we have to we need not to bind ourselves to positional number systems. We have to see that what is the end goal. If the end goal is not addition, not arithmetic, but only a representation of a count, or my end goal is counting, not the multiplication, not division, or not square root, not other operations, but only a representation of a number, then we can choose any of these codes, or maybe we can invent our own code to represent a number so that we can meet our goals. Goals could be power, goals could be having less possibility of error, or goal could be easiness of representation, or it could be aligned to the hardware which we are going to interface with. So with this, like we have now know we now know that how different representations could be there. Now let us say we would like to answer one more question, that what if I would like to, I don't want to only represent numbers, but I would also like to represent characters like A, B, C, or even the special characters like percentage, ampersand, or plus, sign of plus, sign of minus. Now you know the answer already, because all the textbooks so far you have studied before coming here in this class. You have seen numbers, ASCII numbers, and especially in your GEL class of computer science, introduction to computer science, also you have seen these ASCII numbers. So these ASCII numbers are commonly used to represent any kind of a characters, or any kind of a special character which are there on the keyboard, or commonly found characters. They also use these control characters like enter, tab, all those things. So they are representing characters, and to represent each character they use these 8-bit numbers. Okay, now and if I have an array of characters, that also you know that let's say we call them strings, and then we use consecutively these 8-bit numbers or array of bytes to represent a string. And then again one more thing there, that let's say I don't want to only understand the characters which are given in this English keyboard. We are Indians, so there we should be able to represent Hindi characters, Punjabi characters, and we have at least 18 other languages which are notified in Constitution, and 100 other languages which are not notified. So to represent any character in all those languages, we require some extended set. So this extended set is the one which is popular, which is standardized, is called UTF-8. So in UTF-8, it can have more number of bytes. So instead of 1 byte would be as same as ASCII character, but rest there could be other bytes which could be represented, which can have the extended coding. Okay, so this UTF-8 and UTF-16 both have been standardized by standardizing bodies, and it can be used to represent all the extended character sets which is possible anywhere in the world. So there are some languages which has so many different kind of bytes and characters representation. So this UTF-8, UTF-16 can be used to extend, can be used to represent almost any kind of letters which are there in any language in the world. And people keep on extending. If there is a new character, for example, some couple of years back rupee symbol was introduced, so that was also added to UTF-8 and UTF-16, so that we can add these new symbols also, which can be standardized by computer programs, and this standardized information can be used for printing. So this way we can we have almost seen any kind of information could be represented using binary numbers. Still, one question remains. In starting of this course, we said that binary numbers means they would be quantized, they would be discrete. Does it mean that I cannot represent a real number? A real number means a number which would have decimal points, rational numbers or irrational numbers. Irrational numbers means they could be infinite number of digits after decimal points. So can I represent those real numbers, numbers which are not quantified or which are not quantized or which are not discrete in nature? If we can't represent real numbers, then our computation would be severely limited to integers. Okay, so this is the question we'll try to answer in our next lecture. So far, thank you very much, and enjoy doing your exercises and tutorials. Thank you.